Today we are explaining its working principle and DIY instructions. The compact VLF antenna is pretty powerful. Together with a transforming balun, they are already delivering a decent signal. On Electronics Unmasked, we built and tested several 2-meter wire loops, achieving excellent reception on LF and VLF. Today, we want to build a compact VLF loop with just 1 meter in diameter. Thanks to an improved Q factor, it's pretty powerful. I had the best reception yet of the historic transmitter SAQ Grimeton, and I'm really having fun determining the direction of VLF signals. You might have seen the earlier video about it. Let me briefly explain its working principle, and then I'm showing how to build it. Before I'm going into detail, I'd like to give you a hint. At PCBWay, you will find great products and services for everything related to electronics. In their video section, you can learn more about it. I'm always impressed by their shared projects platform. Again, fantastic new projects have been added. And PCBWay is offering an attractive sponsorship program. Take the easy way with, you name it, PCBWay. Direct comparison is the best way to assess the performance of antennas. Based on the measurement results of one category, I'm using these diagrams to estimate the performance of larger or smaller categories. There are other aspects to consider, but in general, large antennas are delivering stronger signals than small ones because their effective area is picking up more power for a given field strength. A wire loop is the simplest way to create a large effective area. Just check out our DIY-friendly suggestions in the earlier videos. Now there are ways to make loops more efficient. You can squeeze out a few more dBs using a wide conductor instead of wire, but there are physical limitations of the method. In case you can accept narrow bandwidths, tuning a loop to resonance seems more promising. Resonance is increasing voltage depending on its quality factor Q. Simply put, Q is the ratio of the energy stored in the circuit to its loss per oscillation. As energy is swinging back and forth between inductor and capacitor, part of it is lost through its ohmic resistance, radiation resistance, and the signal coupling to the receiver. Using the resonance formula, I'm substituting the capacitance C in order to later explain the maximized Q factor. In this calculation, the radiation resistance can be neglected since it's so small in the VLF range. R ohm stands for losses in the loop, capacitor and contacts. 50 ohms divided by the transformation ratio represents the coupling to the receiver input. Now let's quantify Q. I tested ceramic as well as film capacitors and found that both are suitable for this purpose. Film capacitors have lower losses and better temperature stability, but ceramic capacitors have an amazing property I never would have expected. Many thanks to Georg for pointing this out. I will come back to it in a separate video. Their equivalent series resistance, ESR, is about 10 to 30 milliohms in the VLF range and about 3 to 10 milliohms in the LF range. Let's assume 10 milliohms at 20 kHz when connecting several capacitors in parallel. A 1 meter single turns loop's inductance is about 4 microhenry, corresponding to 0.5 ohms reactance at 20 kHz. Its circumference is 3.14 meters. Subsequently, my 2.5 square millimeters copper wire has a resistance of 27 milliohms. Due to the skin effect, its effective conductive area is a bit smaller though. Applying the formula derived earlier to the single turn yields a Q factor of 5.3 at 20 kHz, corresponding to a resonant gain of 14.5 dB. I should add that this applies when the output coupling equals the internal resistance, or in other words, when the impedance is matched for maximum signal. Here is a factor of 20, since Q is a voltage ratio. Now let's consider a loop has 5 turns. While its ohmic resistance is growing proportionally with the number of turns, its inductance L is increasing quadratically. As an effect of this, we are getting a 25-fold reactance and a 5-fold ohmic resistance. The Q factor thus grows to 32.5, which corresponds to a resonant gain of 30.1 dB. That sounds pretty impressive, doesn't it? These are the ideal transformer ratios for 1 and 5 turns. But I will come back on that in a minute. Basically, I'm connecting the 5 conductors of a cable in a loop, having the properties we just mentioned. And then a capacitor and the balloon's primary winding are connected in series. Incidentally, 1.14 microfarads are required for the SAQ Grimeton frequency of 17.2 kHz. Previous experiments were showing that 5 to 6 turns are optimal for the primary winding. That's why I came up with the idea of routing the loop directly through the ferrite core to minimize losses. It's just a rigid electrical installation cable. The balun is made of 3 bonded toroids. Each core has a permeability of about 3 microhenry per square turn. As mentioned, for a 50 ohm receiver, a transformation ratio of 256 is suitable, being achieved with 5 times 16 equals 80 turns on the secondary winding. In that case, you don't actually need a coupling capacitor. If your VLF receiver has a higher impedance, like mine, then a ratio of 576 corresponding to 120 secondary turns is better. But when connecting the antenna to 50 ohms or when I'm operating at higher frequency, I need to reduce the coupling by the series capacitor. In doubt, switchable turns make sense. My balun fits into a small junction box. Conductors are soldered in a loop separated by this white insulator. And capacitors are connected using the terminals with the knurled nuts. Now it's getting exciting. Just keep an eye on the signal level while I'm switching from my 2 meter non-resonant loop to the new 1 meter resonant one. Wow, it's receiving a much stronger signal and signal-to-noise ratio. That's fantastic, isn't it? Let's put that into perspective. In the non-resonant mode, it would be on the yellow level. And now its signal level and SNR is 13 dB greater compared to the 2-meter loop. Incredible! When tuned to the receiving frequency, it can compete with loops 4 times larger. Now let's look at the antenna's out-of-band rejection. I'm receiving 0 to 4 MHz here. Our VLF signals are located on the left within the first millimeter. All other signals in the 4 MHz range could potentially cause intermodulation. The resonant loop's out-of-band rejection is at least 15 dB better. This can be a significant advantage when you're having strong transmitters in your vicinity. The compact antenna with improved Q is really fun. By the way, be sure to check out the other video on direction finding. In an upcoming video, I'd like to try a rigorous Q optimization to unlock the full potential of the method. Furthermore, there are ideas for convenient frequency tuning in our pipeline. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.